Hello and welcome to our first live session for this course. I'm very happy to be back in front of camera. The lectures that you have been looking at have been recorded some time back. You may notice some change in my appearance. So thanks a lot for coming and for asking questions. I already see that there is one question by Pratyush who asks whether proof of infinitude of primes can be explained. So yeah, it is indeed a good point to begin with. So all right. So finite set is something which is in bijection with the set of integers up to some n. So you have 1, 2, 3, 4, 5 up to some n. So let's say 2023. If you have any set which is in bijection, so there is a 1-to-1 onto function from your set to this set of say 1 to 2023, those many integers, then we say that the set is finite. And if your set is such that it cannot have any bijection with any such set for any n, okay, then we say that it is infinite. Correct? So the definition of finite set and infinite set, they are clear to us. To show that something is infinite, on the other hand, to begin with, if you want to show that something is finite, then that is very easy because you can just get some set 1, 2, 3 up to n, show that your set is in bijection with that set, and then your set is finite because it will have bijection will preserve cardinalities. So it will have n many elements. And so to show that some set is infinite, you have to show that it is not finite. So of course, you have to show that it's not an empty set, and then you should show that there is no bijection from your set to any 1, 2, 3 up to n. Okay, this is what we will have to do. So now what we do for primes is that we assume, so this is the method of contradiction that I like a lot. We assume that our set of primes is finite. Okay, so there will be some 1, 2, 3 up to k. I think I have used the notation k. So you have P1, P2, P3, P4 up to Pk. These are the only primes. Okay, so we have finitely many primes. This is our assumption. And we will later get a contradiction by showing that there is one more prime which we did not count in this set of k primes. Okay, so since this can be done for any finite k, we will have that no matter what k you take, there is always a prime outside this k primes. And therefore, the set of primes cannot have k elements. It will always have element more than k for any k. And then it is an infinite set. Okay, that's the simple basic idea. Okay, so now we have this P1, P2, P3 up to Pk. Those are the first k or whatever. We have our k many primes. What we do is that we take the product of these primes. So we have n, which is a new number we are going to define, P1 into P2 into P3 up to ... pk. So we go take product of all these k primes that we had to begin with, and we add 1. So we constructed a natural number, which is the product of these k primes, and added 1 to that number. Now, because this is a natural number and we have proved that every natural number should have a prime factor. That prime factor can be itself. It can be n. That itself can be a prime factor. Or if n is not a prime number, then it will have smaller factors which are definitely primes. So there is a prime which divides n because n is bigger than 1. If any natural number is strictly bigger than 1, then it has to have a prime factor which can be itself or a smaller number. Okay. So this new element capital N, which is P1, P2 up to Pk plus 1, that will have a prime factor. You call that prime factor to be P. And now my claim is that this P cannot be one among the P1, P2, Pk. It will have to be one more prime than the primes that you had initially. Okay, so how do we see that? Because your small p divides capital N, and if it was one of the P1, P2, Pk, then it will divide the product P1 into P2 into P3 up to Pk. But then it will also divide the difference of those two numbers, which is equal to 1. And that's a contradiction. You cannot have a prime number dividing 1 in integers, because prime by definition are numbers which are bigger than 1. Okay, so that's the way, Pratyush, one would see that the set of primes cannot be finite. The set of primes will therefore have to be an infinite set. So thank you, Peter, Jasu. So namaste to you also. And Chaitra wants to know, sir, it would be a great help if you could explain in a little detail on the induction hypothesis you use in the proofs, different from the one I am familiar with. Okay, yeah, so this may happen. So, induction can be seen in many different ways. One way to see induction is that you assume some statement to be true for n, and then you prove it for n plus 1. This is one particular induction hypothesis that we have. Another way to say that is that you would assume that something is true for all integers up to n. So not just for n, but for 1, 2, 3, and so on up to n, all of them. And then you prove it for n plus 1. This is another induction hypothesis, and both are equivalent. So if you have one statement, which you call statement A, that statement A would be that if a statement is true for all integers up to n, and then it is true for n plus 1, then the statement is true for all the integers. This is statement A. Statement B is that if a statement is true for n, then it can be proved that it is true for n plus 1. Then the statement holds for all natural numbers. Okay, this is the statement B. So you may assume statement A and prove statement B, or you can assume statement B and prove statement A. Those are very easy and very interesting exercises in logical thinking. So this is how one would prove induction hypothesis. I must also say that whenever you have induction hypothesis, there is a very, very, very important step, which is that you have to verify that your statement is true at some beginning stage. Meaning it can be any n, it doesn't have to be 1. Your statement might be true for 10 onwards. In that case, you will have to prove that it holds for n equal to 10. And once you have that, then you can use our induction hypothesis. Okay, so the method of induction has two parts. You have to have a beginning process. You have to begin the induction at some integer. And once you begin, you have to have a machine which allows you to go from n to n plus 1, or from whatever numbers less than n, all of them starting from your beginning integer, and then you are allowed to go to n plus 1. So induction, the method of induction is actually these two parts. So beginning stage cannot be forgotten. You should not forget that particular stage. Okay. There are some very easy counter examples which say that, if you don't take care of this initial stage, then some very weird statements can be proved by induction. Okay, just this induction hypothesis, whenever it's true for n, then it's true for n plus 1. If you just go on using this blindly without beginning with an initial stage, then there is no way. Meaning, if you don't have the foundation, the whole proof will collapse. There will be nothing that will be left. This, I hope, answers Chaitra's question. Okay, Siddharth, hello. He says, in the proof of if AB equal to AC mod n and B is C mod n, if A and n are co-prime, what if we do n divides AB minus AC implies that n divides A into B minus C. Since n does not divide A, we should have n divides B minus C. So B equal to C modulo n. What happens is that when you have product A into B minus C and you have that n divides this A into B minus C, you can have that n does not divide A and n also does not divide B minus C. That can happen. For instance, your n can be 6, A can be 2. and b minus c can be 3. Okay, your b can be say 8 and c can be 5. All right. So if your a is 2, b minus c is 3, then a into b minus c happens to be 6. So your n, which is also 6, will divide this product. But n does not divide any of the a and b minus c. To have that n divides b minus c, it is important that you have n and a are co-prime. Meaning the point here is that we have this statement for only primes, that when a prime divides product of two numbers and the prime does not divide one of them, it will have to go and divide the other. That statement is not true when n is not a prime. So our example here is n equal to 6. It divides 2 into 3, but it does not divide 2 and it does not divide 3. So yeah, some small cares one has to take. It's a bit of a subtle thing. But if you take some small care, then everything goes quite well. So that I hope answers Siddharth's question. So Purnima asks when to use which way of induction. I mean, how to know whether it is the case of simple induction or of complete induction. I think, meaning typically, it's not even clear that one has to use induction. In many places, the proof, if you want to solve a problem, you have to really have a lot of practice. And once you have a practice, then by looking at the statements, you will be able to see whether you can use induction or you have to use something else. All right. So having a practice is first of all very important. Second thing is that you will try to use the easier method, which is the, having the statement true for n, then the statement is true for n plus 1, and try to use that. That is, I think, what you mean by simple induction. You try to use that, but then you may realize that in your proof, you may sometime have to assume that the statement is also true for n minus 2 or n minus 3. And then you have to use for not just for n to prove the case for n plus 1. You may have to use also some of the previous cases. And then you have to use all of that. But it's not a big deal. Meaning to use induction, what you should do is that straight away prove it for the beginning integer, which can be 1, which can be 2, or whatever number you are beginning. It can be even a negative integer. So prove it for the first integer, and then you start doing the proof n implies n plus 1. In the meanwhile, in that proof, if you require something smaller than n, assume that and continue. So if the simple induction works, very good. We don't have to do too much work. If it doesn't work, then we use the complete induction. That's how it would happen. Okay. So that is proof. Siddharth says, wanted to understand what is wrong in above since we have a long proof. Yeah. So, the thing is that n, if it's not a prime, then what can happen is that when n divides the product, some of the prime factors of n can divide one factor of the product, and other prime factors can go and divide the other things. Okay, so therefore n dividing b minus c, which is what we want, because we want to say when ab equal to ac and a satisfies some properties, we would like to cancel that and have b equal to c modulo n. This is what we want to have. In this case, we want when n divides ab minus ac, we should have n divides b minus c under some conditions on a. And the conditions are that a be co-prime to n, that there be no prime factor in common. Because if there is a common factor between n and a, then we don't have guarantee that n will divide b minus c. And there are examples as I have just explained. Okay, good. So Siddharth is happy. Divakar Prajapati, hi Divakar. So you have asked this question, a square minus 1, b square plus 1 and a square plus 1, b square minus 1 are the same. This is not true. In fact, I have sent out an email in the discussion forum saying that this was incorrect. And in fact, there are very easy examples which will say that these two numbers are not correct. So there must have been something else in my mind when I put this question. There are something called symmetric functions. So if you are looking at, instead of this, if you were to look at a square plus b square, a cube plus a square b plus ab square plus b cube and so on, these are the symmetric functions which don't depend on what a and b you take, whether it is a or b and whether it is b and a. So I must have had something in mind of that kind, and so therefore this is certainly not true, as Divakar also has pointed out. Okay. Purnima asks, is induction valid for proving something related to natural numbers only? Can I use for real numbers? So typically, induction involves a jump at some stage, meaning you can prove it for a discrete set. You can prove it. I'm not even sure if you can use it to prove some statement for rational numbers. But if you have something of the type which are all multiples of 1 by 2, then there you can use induction. Typically, what happens is that, this is not said, but this is also called method of finite induction. So this method is called method of finite induction because the step always involves k plus 1 and so on. So when you have a finite set, then the statement is true. And when we say that the statement is true for all natural numbers, it just means that whenever you take any number, that number is a finite number. And then for that it is true. So there is a generalization of this which is called transfinite induction, or what is also known as Zorn's lemma and so on. So there are some statements which are equivalent to each other. They can be used to prove statements on real analysis for real numbers. Okay, so in general, when you have natural numbers or you have some infinite set which is countable and also discrete, meaning just having rational numbers, for instance, will not be enough. You should have your set to be discrete. There should be jump from a number to the next number, then from there to the next and so on. Then one can, I believe one can use induction for that. Ishwar Panchakarla asks, sir, paper pattern, how many MCQs? Typically, when we have the final examination, then I do not give MCQs. Because what I would like to see is how you compute questions and what are the answers that you write. So that is how we will have. There may be some number of MCQs, but there will also definitely be some long questions that I would want you to, take pen and paper and do some good mathematics, some very interesting mathematics. So Siddharth says, if there is one book which you could recommend for number theory, so on our course webpage, there is a book by Alan Baker that I have already suggested as a very good book. There are many other books which are interesting, but I think, what my course, the whole structure and so on, this is based on this book by Baker. I think I don't remember the title now, but I think it's called A Comprehensive Introduction to Number Theory. So Alan Baker, one of the very, very renowned number theorists who passed away recently. So this is a book by him. I think this book will be very useful. Peter Jassu says every prime number is of the form 6n plus minus 1 except 2 and 3. Sir, this is true. And yes, sir. Yes, sir, Peter, sir, this is true. Of course. So, meaning the thing is that if you have anything, so modulo 6n, modulo 6, your numbers would look like 1, 2, 3, 4, 5, and then 6, which we call 0. So your numbers will be 6n plus 1, 6n plus 2, 6n plus 3, 6n plus 4, 6n plus 5, and 6n plus 6, which is a multiple of 6, right? So this multiple of 6, you don't have to consider. There is 1, 2, but even the 2 can be ignored because it's an even number. And once you go beyond 2, then no other even number is a prime. So 2 is gone. Similarly, 6n plus 4 is gone. You are looking at natural numbers. Okay, so all of these are even numbers bigger than 2. 6n plus 3 is always going to be a multiple of 3 unless n is 0. In that case, n is 3, but I think Peter has been very careful to take 3 out. So that is also gone. And so the numbers which are left are 6n plus 1 and 6n minus 1. So every prime other than 2 and 3 are of the form 6n plus minus 1. In fact, I would say that this statement can be very easily generalized. You can have any number n, and you will say that outside a set of finite primes, finitely many primes, every number has to be a modulo n, where a and n are co-prime. For instance, if you start with the number n equal to 10, then any prime has to be of the form 1 modulo 10, 3 modulo 10, 7 modulo 10, and 9 modulo 10, except 2, 5, and that's all. Okay, so the multiples, the numbers which divide the number you started with. So here we started with 10, Peter started with 6. So you have to take the prime factors of that number out. Once you have that, then all the remaining primes will have to be of the form a modulo n, where a is smaller than n and a is co-prime to n. Okay, good. Divakar Prajapati says some prime number is of the form 4k plus 1, but can we know n? Divakar, do you want to explain this question, meaning what is that n instead of 4k? You want to some, there are some prime numbers, of course, of the form 4k plus 1, but can we know n? So what does this mean? Does it mean that what is the k? No, but once you have a prime and you know it is of the form 4k plus 1, you can easily find that k. Maybe he wants to know whether the prime is which n we want to know. Yeah, let me see. So let us wait until Divakar explains his question a little more. Meanwhile, there were some questions which were asked in the form that was circulated. So one of them, there are, some general questions. One of them asks for when will the answers to the assignments uploaded. So I think, there is typically a deadline for submitting the assignments. Once that deadline is passed, then our team of IIT Bombay NPTEL will upload the answers. I have already provided the answers to them. So they know they have this timetable ready with them. They know the assignment solutions for each week are to be uploaded and so on. So once the course starts and gets into the rhythm, then these things get done every week. So I think if today or yesterday was the deadline for the assignment 1, then typically today or tomorrow the answers are uploaded. Okay, but the answers, once again, the answers are not in great detail. We just tell you which options were correct. If you want to know why some certain options are not considered correct, or if you want to have a discussion on these questions, then our discussion forum is there exactly for this purpose. So please, I would request everyone to come and have some discussion on this so that, even though we have the answers, it's a nice way to discuss how we reach these answers. So it's a very good thing. Okay, so he asks, can we make a set of natural number for which 4k plus 1 is a prime? So he perhaps wants to know what are the k's for which 4k plus 1 is a prime, and that we don't know whether, whether you can explicitly find out all these k's where 4k plus 1 is a prime. I think that is not a very well understood question. So Peter Jassu is saying n plus 1 by 2 is an integer for every n belonging to z. It is true. I don't know whether he is asking whether this is true or whether he is asserting that this is true. I don't know about that, but I would suggest that, let's not discuss things which are related to assignments, because this is perhaps part of assignment number 1, or what? It's part of assignment number 2. So now, meaning I have already assignment 0, assignment 1 and assignment 2 are out, and I am in the process of typing assignment 3 and maybe some more assignments. So I don't exactly remember, but yeah, meaning perhaps this is not part of assignment 2 and it may be part of assignment number 1. Anyway, Peters Jassu says it is true. I think he will have a proof. Meanwhile, let me go to this statement of Jay Kumar, where he asks whether real number, rational number. I think this was a question from assignment number 0. Yeah, the real number, integer, and rational number. So this is something we can discuss. So, there are the set of numbers is a set which is increasing, and you have natural numbers. When you add 0 to that, then you have something which is called whole numbers, as we learned in school. I don't know if it's taught in the same way even today. When you add the negative numbers, you have the set of integers. So you have negative numbers, you have 0, and you have positive numbers. All of them constitute the set of integers. Then when you have integers and you divide them by non-zero integers, what you get are rational numbers. So you have integers which are contained in rational numbers. For instance, 1 by 2 is a rational number, but it's not an integer. Okay, so the set of integers have more elements than the set of natural numbers or even the set of integers. Now, real numbers is a very big set. So there are some ways to count the number of elements in the set. We have, of course, the finite sets. Then there are infinite sets, but even the infinite sets come with some hierarchy. There are some sets which are strictly smaller than another set, which look infinite, but they are strictly smaller in the sense that there is no bijection from between those two sets. So they will have different cardinalities. So real number is very big compared to rational numbers. So there are definitely real numbers which are not rational. And one standard example is root 2. You take root 2 and you can assume the fundamental theorem of arithmetic, which is that every natural number bigger than 1 is a product of primes, and then you can write it in exactly one way up to rearranging the primes. If you assume that, then you can prove that root 2 cannot be written as p by q for any p and any q. Okay, that statement I think follows quite easily. Since I don't have any further question, I may as well explain this statement. So if you want to write root 2 as p upon q, take the q to the other side. Okay, so you have q into root 2 equal to p. And now you square both sides. So you get 2 into q square equal to p square. Okay, so now left hand side has 2 as a factor. Right? So the 2 should divide p square. But 2 is a prime. So when 2 divides p square, it has to divide p. And therefore, when the 2 divides p, so p square will have 4 as a factor. So there is one more 2 on the left hand side. 2 into q square, we saw only one 2. The second 2 is also hiding somewhere because 4 divides the right hand side. So 4 has to divide the left hand side. 4 is 2 square. Out of them, only one 2 is seen. So the second 2 has to come from q. But if 2 divides q, then 2 square has to divide q square. And so you have one more 2 which has come out. And that way you can just keep going and this process will never stop. Another way to look at it is that when you have 2 dividing q, the number p by q, which you wrote as a rational number, already has a prime factor for both numerator and denominator. And you can begin with, when you wrote root 2 equal to p by q, you may say that we write this with the assumption that p and q have no common factors. If you have any common factors, just cancel them out. Okay, this is the way, when you are writing a proof, then after having reached halfway through, you realize that you have to add one more statement to the hypothesis. Then you come back and put it there and continue with the proof. Okay. So to say it again, root 2 cannot be written as p by q, where p and q have no common factor, because it gives you 2 into q square equal to p square, where 2 divides p then, and therefore 4 divides p square. So 4 divides 2 into q square, and therefore 2 has to divide q. It divides q square, so it divides q. And then you have a common factor between p and q, which cannot happen. Okay. All right. So no other questions. So let me go to the questions which were asked to me in the form. Yeah, so this is also another common query that I get, whether some lecture notes will be provided. So I think in a question asked today on the discussion forum, I have replied saying that you can go to the course website. On the left hand side, you will see a panel where you will see week 1, week 0, week 1, week 2, and so on. And below everything, you will see download. So if you click on download, that will take you to a page where you can see videos. And again, there will be one more link called downloads. and if you click on that, then you will be taken to what are called transcripts of my lecture. So, the technology is very good. So whatever I have spoken, the YouTube has recorded it, or perhaps NPTEL people have spent too much time and efforts into it, and they have recorded it. And those are the transcripts of my lecture. So whatever I have spoken, this is recorded and typed, and that is the PDF file which is available. But it comes with all mistakes and everything. I may make mistakes, I backtrack and so on. So all of that has come in that. So, be careful while reading it. That is all that I will say. So those are the PDF files which are available. There are no lecture notes which are available as yet, because perhaps I will make them available when I run this course 2-3 times and so on. And whenever I have more time, I may make the lecture notes available. The basic point of not making lecture notes is that, there are many good books. Just now, who has asked, Siddharth has asked whether there are good books, and indeed there are many good books. Many Indians also have written very nice books. So what's the point of adding something more to the set which is already sufficient? That's the point that I have, and therefore I did not make notes. Another thing is that I have seen this, even here in IIT Bombay and some other places, both in India and abroad, where I have given lectures. If the notes are provided, then there is a tendency to not attend lectures very carefully. Although I know you are very serious people and you will still attend all the lectures, still, perhaps I will make the lecture notes available some other time, but they are not available right now, and it will be difficult for me to make them available right now because I have some other work pending also, and so please excuse me this time. Okay, so this is another question. Is there some positive integer n such that n plus 1, n plus 2, so on up to n plus 200 are all composite? And explain. So I believe this M is a teacher, because he has asked this question as one would ask a question in an exam. Because typically, if you ask a question like this, whether some such thing holds, then students may just say, yes, it holds. Or they may say, no, it doesn't hold. And that's all. And when you have an experienced teacher, then you will say, explain or justify and so on. So indeed, there are numbers. There is a number such that n plus 1 up to n plus 200. These are all composite. So how do we prove this? So let's see, meaning of course I can give you the n. There is a formula for this n, but let's try to reach this n. So how do I want to prove it? Suppose, so there is that 2 which is coming there, right? So n plus 2 has to be a composite. If you want n plus 2 to be a composite, what we should have is that 2 divides n. That is something which is important, right? Otherwise, we cannot say that it is a composite number. If n plus 2 is odd, then we are not sure whether it is a composite number. But if n plus 2 is an even number bigger than 2, then we know it is composite. Okay, so 2 should divide n. Then after n plus 2, there are those 3 dots. So that would mean that everything from 2 to 200 will come. So after n plus 2, there is n plus 3. So 3 should also divide n. So that you will have that n plus 3 is a composite number. To have something which is composite, you should have that it is divisible by some small primes and also have some factor which is coming out. So, for instance, if n is bigger than 2, then n plus 2 will be bigger than 4. And so when you divide it by 2, something else will be there. It will not happen that you will have n plus 2 equal to 2 into 1. We want to avoid such a thing, okay? So n plus 3 should also be of the form 3 into something, and therefore 3 should divide n. Right? So when you have 3 divides n, then you know that n plus 3 will be composite. N plus 4. When is n plus 4 composite? When you know that 4 divides n. Similarly, up to n plus 200, when do you know that n plus 200 is composite? When you have 200 divides n. Exactly, that's when you know that it's going to be a composite number. Okay? So we started with n. We want n, n plus 1, n plus 2, so on up to all of them are composite. And we reached the condition that we require for this to happen, which is that 2 should divide n, 3 should divide n, and so on up to 200 should divide n. So this 2 into 3 into 4 up to 200, which is 200 factorial. This is the number. So if your n is 200 factorial, then n plus 2, n plus 3. If it's 200 factorial, n will also be composite. Correct? So n is composite, n plus 2, n plus 3 up to n plus 200 are composite. The only thing we are not sure about is n plus 1. Right? Because if you have 1 dividing some number, that doesn't mean that n plus 1 is composite. Okay, so what do we do? So what we do is that we take n plus 1 as some k plus 2. So we will start with some number. Instead of starting with n, you can start with something plus 2, for instance. Okay, you just want a set of 201, right? You started from n plus 0, n plus 1 up to n plus 200. You want a set of 201 composite consecutive numbers, which are all composite. So all you have to do is that choose that n carefully. Maybe you will have to take 201 factorial. So that when you start with 201 factorial plus 2, 201 factorial plus 3, and so on up to 201 factorial plus 200. And also you can add 201. You get a set of maybe now 200 consecutive numbers, which are all composite. So be careful about this one. You know, sometimes you may start doing things and it may seem that things are working very well, but some small numbers, you may have to take some special care. So once you take that care, then it will work. Good. Okay, so let me go back and see if there are any questions which are asked. So somebody has asked, is question 2, option 4 correct, and so on, which of course, once again, I will not tell now because it is something, first of all, I don't know which assignment we are talking about, whether it is assignment 1, assignment 2, that is not been said. But anyway, we will not explain the assignment questions at this moment. Okay, so there are no questions that are pending here. So let me just start discussing on various things on my own. Of course, if you have any further question, feel free, and that will give us some direction in this discussion. So I think, you know, I have already said in the beginning that there are a few important themes for the course, and the theme number 1 is the theme on primes. And indeed, there are many interesting results. As we have seen, there is the most interesting result in this theme is the prime number theorem, which says that, you know, it is not easy to see how we can count primes, but there are asymptotic formulae for counting primes up to some real number x. Okay, so Siddharth has asked something slightly outside this course. Can you suggest an elementary level book for algebraic number theory? Okay, so that's a good question, of course. So Peter Jassu has asked, is n factorial plus 1 always prime? So it is often not a prime, but you cannot prove that it's never a prime. I think sometimes maybe it is a prime. If you take 3, n equal to 3, 3 factorial is 6, and 6 plus 1 is a prime, which is 7. So we don't know. 4 factorial is 24. 24 plus 1 is 25. This is not a prime at all. So I think this is what Divakar has also answered just now. So indeed, n factorial plus 1 may not be a prime, but sometimes it can be a prime. We don't know. I think this is perhaps a nice thing to conjecture, to see that there are infinitely many primes. Maybe this is already a conjecture by somebody's name. So, okay. So coming back to, okay, so M has asked one more thing. 3, 5, 7 are the only 3 consecutive odd integers that are prime. How to approach the proof? So I think this is what Peter had already said, that something which is a prime has to be of the form 6n plus minus 1. except when you have 3. So, if you take some numbers which are 3 consecutive odd numbers, one of them will have to be 1 mod 3, other 3 mod, 1 mod 6, another will have to be 3 mod 6, and the third will have to be 5 mod 6. But then, meaning 6n plus 3 can never be a prime unless it is equal to 3. So that tells you that, 3 consecutive odd integers cannot be primes. Okay, so now we come back to Siddharth's question, which is slightly outside this course. Indeed, so algebraic number theory, there are many interesting books. But if you really want to study, so it also depends on what you want to study in algebraic number theory. But I would say there is this book by Daniel Marcus. The spelling is Marcus, and the book title is Number Fields. Number Fields. So this is a very interesting book, a very nice book. This is something you can read. There is also a book by Reuben Boehm, I think, which says, so there are some books which, look at algebraic number theory from the point of view of Fermat's last theorem. So those are also some of the good books, I think. Yeah. So I should also perhaps tell you that there are some excellent sites for asking these kind of serious questions. So there is this Quora, which you will all know, Quora. It's a forum where you can ask questions and people will come and answers. And you also may be giving answers to many of those questions. Then there is something called Math Overflow or Math Stack Exchange. And I'm sure that these basic questions are already discussed there. So, of course, meaning somebody who is a practicing number theorist or a practicing mathematician, that person will give you a better answer. So, it is, of course, a good thing to ask the questions in these kind of discussion meetings. But you can also ask the question to Google, and Google will perhaps take you to Math Overflow or Math Stack Exchange or to Quora, and where you can get some good answers. So, good. If you are interested in learning algebraic number theory, very nice. I'm very happy. Yeah. Okay. So, yeah, so we were discussing primes, and I said that prime number theorem is one very interesting result, which says that, the number of primes up to x can be almost measured. Meaning, in the basic calculus course, we learn about asymptotics. So there might be a curve, which might be a very intractable curve. You don't know how the curve behaves. But what you would know is that after a stage, it is very close to some another well-known curve. And this is what we, say that the well-known curve is asymptotic to your curve, or other way, your curve is asymptotic to this well-known curve. This is something that we say. So there are these nice estimates which are given for counting primes up to some number x. So this is where I say that Gauss, Gauss is touted as one of the greatest mathematicians ever lived. And it is very nice, at a very young age, when he had some list of prime numbers at his disposal, he came up with this result. So, this is why one should do mathematics, because there are great mathematicians like Gauss who have done good work, and we have to just follow with their in their footsteps and do some interesting work. That's all. So this is about prime number theorem. There are many interesting things coming up. We will have congruences. We will have the four square theorem, which will say that every natural number is a sum of at most 4 squares. And we will see generalization of this statement, which will also have a lot of contribution from Indian mathematicians. So stay tuned to the course and continue being interested, continue solving exercises in this course. So that will be something which will be very useful. And I wait for some more questions. Otherwise, I will start some another discussion. Of course, I cannot ask a question here for you to answer. That would not be a correct thing. There is also a human element in all this, meaning, in my courses, in this course, in the lectures, I have said somewhere how two mathematicians, they had some alterations, some differences of opinions, where for who proved what and so on. So that's the human element which comes everywhere. Wherever we go, we see this human element coming. But that's a good thing, meaning these are not superhumans or these are not inhuman people. They are humans. So there are many interesting, these days even Wikipedia may have something, but I will not really believe Wikipedia because, Wikipedia can have incorrect information. I think luckily for mathematics, it doesn't give incorrect information because once some incorrect information goes, then somebody will notice it. But Wikipedia is something which is, which it can be edited by anybody. So once something is there, then someone can go and remove it or alter it and make something else. So Wikipedia is not something that I will trust blindly. But Quora, Math Overflow, these are some of the good sources where you can get information about many such things. I think even for mathematics, there is something called Wolfram. So Wolfram has a mathematic server, and there are many terms of in mathematics are explained there. Sometimes the correct entries from Wikipedia are copied, but so be it. And Wolfram Mathematics Server that also has many good information about mathematics. So that's again another server where you can head to get some information about mathematics. Yeah, so Fermat's last theorem is another theorem. So, after the prime number theorem, Fermat's last theorem, which is something which is single-handedly responsible for, one could say, single-handedly responsible for the latest development in algebraic number theory. And it's a very innocuous statement that x to the n plus y to the n equal to z to the n, and n is bigger than 2, and x, y, z are what are called non-trivial triples of integers, because you can put 0 in one place and then x and y can be same or they can be negatives of each other. So those trivial solutions are taken out. Then there are no non-trivial solutions to this equation. This is what Fermat's last theorem said, which was proved by Andrew Wiles around 96, 97. And that's a very, very important statement because it deals with a lot of further developments in algebraic number theory. I think we should hold Siddharth responsible for me to talk on algebraic number theory, but since there are no questions, I will speak about this. So there are things called elliptic curves and there are things called modular forms. So elliptic curve is something which is an algebraic object, and modular form is an object coming from analysis. So, meaning on one hand, you have something like 1 plus 1 equal to 2 or 4 into 6 equal to 24. So you have discrete structure like this. And on the other hand, you have structure which is a continuous structure like a real valued holomorphic function and so on. I mean, not real valued holomorphic function, but something to do with complex numbers, functions defined on complex spaces and so on. Okay, so these two are related very intricately by something which is called L function. And this is the thing which goes into the proof of Fermat's last theorem. So this was Wiles's childhood dream to solve Fermat's last theorem to give a proof for Fermat's last theorem. Even there we have a small human element, In Fermat's time, French and English people would have a rivalry. Fermat, for instance, would send out some statements to English counterparts, the mathematicians coming from England, and ask them to prove it. And I believe some of the others would do the same way to French people. And in the end, of course, Andrew Wiles, who comes from England, he did prove it. So whatever Fermat had wished for did come true. Yeah, so Wiles wanted to prove Fermat's last theorem. This is what he was really very interested in, and he wanted to spend his time into it. He, in fact, is reported to have told his advisor that he wanted to work on it for his PhD problem, but his advisor, John Coates, he told him that no, that's a wild problem. Let's concentrate on something which we can do, and we will think about it later. And Wiles also realized it while he was, studying mathematics. He realized that with the tools he had in his hands, it will not be easy to attack Fermat's last theorem. And he continued working on those things for a while, the things that he learned during his doctorate and so on. And then there was this mathematician by name Gerhard Frey. It is Frey. I believe he's a German mathematician by his first name. And so Frey proved a result which is, which was saying that if something happens, then Fermat's last theorem would be true. That's the result that Frey proved. And then there was one more result by an American mathematician by name Ken Ribet. And so then it became clear to Wiles that all he had to prove was that statement which Frey had put. So once that statement is proved, which is now a statement which luckily fell in Wiles's expertise or in mathematics. And once he had that statement, he could work on that. And although meaning I'm putting it in a very simple way, but working on that was not easy. He worked on it for 7 long years in solitude. He could not tell anybody for that. He couldn't share it with anyone except his wife and his family members. And yeah, so then he proved it ultimately. There is one more small hiccup he faced, but he overcame that with the help of his student and he had a proof in the end. So mathematics is filled with many such romantic stories, many such nice, fantastic stories. And that's what makes mathematics very interesting. Okay, so I'm waiting for questions to come. If there are no questions, I will have to keep randomly talking about various things or look at the form and see whether someone has asked me a question. Okay, all right. There is one question. 1 second, Purnima. There is another question which has come here. Sir, how much we can compress the Bertrand postulate interval so that we can always have a prime number in that interval? This is an interesting question. So I don't now remember if I told you about Bertrand's postulate in the course. Bertrand's postulate says that you take any x which is bigger than 1. Okay, you take any real number x which is bigger than 1. Then there is a prime number inside the interval x to 2x. And the question is, how much can you compress it? Can you say that there is always a prime number between x and 1.5 times x? Of course, you would think of 2 and 3. So x is 2 and 1.5 times x is 3. But then you can say that you will look at x bigger than 2 and ask whether this holds. Maybe there are some easy counter examples because I think, once you have 3, after that, to get the next prime, you have to go all the way to 5. So it is perhaps possible to have, yeah, so you can have 3 and 4.5. So indeed, the gap cannot be made very small. I think this is what also goes into Bertrand's postulate that the x and alpha times x, where there is always a guarantee of having a prime in this range, then alpha has to be 2. Perhaps my personal opinion would be to say that it cannot be made shorter. Okay, this is what I believe. I hope I have explained it to my viewers what Bertrand's postulate is. If you have any more doubts on it, please let me know in the chat session and then I will be happy to speak for some more time on that. So Purnima is asking, so sir, your discussion reminded me of online course I did some time back, fun with prime numbers on edX. Now I have forgotten most of the content. Any suggestion to remember content of online courses? How would you remember something which you have done back? Maybe that's the question one would say. So yeah, I think most of us forget things, meaning if you have done something long time back and haven't thought about it in a while, then it is not easy to remember that. Although, meaning there are exceptions and exceptions perhaps prove the rule. There are people who would remember everything and each and everything said by somebody or other. So let's take those exceptions out. But I think, to remember something is basically what I would say is that even if you come across some statement and you remember that this statement was done in that course, even if you remember this, and then to know more, you can always go back to the course and look at it. That is something you can do. So even this thing, if you can do, then that would be good. So, many of us have a lot of books. Just to give you a somewhat different analogy, many of us have a lot of books. Meaning, if we were shooting this video in my office, then you would see in the background many shelves with filled with books. So we have those books, and meaning humanly, it is not possible to read all those books, but we browse through them. And typically, whenever some mathematical fact comes up, then we know which book we have to look at. Okay, so that much we should remember. And to do that, we should keep thinking about it. Meaning, typically, how would you remember about something? You would remember about things because you keep thinking about it. People, there are some people who would remember perhaps all centuries that Virat Kohli has scored, or all centuries that Tendulkar has scored, or some of the interesting incidences that happened. So, of course, there are some interesting happenings, there are some events which happen, and then they get inked on your brain. So then you will remember them. But even otherwise, you have to think about them. You have to keep thinking about it. You have to meditate upon it. And, to go beyond this, I will say that if you like something really a lot, then you will remember it. So perhaps, meaning it would not be possible to suggest, there is no formula. We cannot say do this and then you will remember everything that you have done in the online course. Maybe something different in the course videos would help, but those videos are now done, so I cannot go and change those videos. But yeah, meaning thinking about it will definitely help. Learning about it. Even now, if my discussion has reminded you of some course, I think that's a very good thing. It means that you haven't completely forgotten about that course. It's not that, oh, did I do that course? That's not a question that you had. So I would say that it's still a good thing. Good. It's close to 5 o'clock. If there are some more questions, I will be happy to take. Otherwise, I will have to ask my team whether we are allowed to go beyond time or whether we have to finish by 5. Of course, you would also have many important things to do. So, Ravi, are we finishing at 5? We finish at 5 or now we can finish? Okay, all right. It was very nice talking to you. Next time also, please ask questions. Your questions are the one, on which this whole thing is running. Typically for any vehicle to run, we will need some fuel, but these discussions run on questions. So please ask questions, and I hope I have answered the questions. If there are any more questions which you think of after this discussion session, then please feel free to write them in the discussion forum. So see you.